All right, so yesterday I talked about the power rule, and pretty much the summary from yesterday was the only thing you know how to deal with is if it's a number x to a power, and as of yesterday, that's all you know how to deal with. So no matter what I give you, you need to make it where it looks like number x to a power. And if you've got a bunch of terms, if you're adding or subtracting them, you can sort of take the derivative of each term. But when we look at this, I don't have number x to a power, and I don't have this as like a single polynomial. So I've got to make it look like something I can handle, which means I got to do some algebra. So I do some algebra, and I end up with 15x plus 12x squared minus 10x squared minus 8x cubed. And I end up with y equals negative 8x cubed plus 2x squared plus 15x. Now I've made it look like something I can deal with, and now it's just a matter of taking derivative term by term. So y prime equals negative 24x squared plus 4x plus 15, and we have successfully taken our derivative. Yay, right? Now, this, I was just to give you this problem actually is not the goal for today. This is kind of a little summary for what I did on Tuesday, and it is going to lead into something I'm going to talk about. Now, what's happening today is we're going to learn about different techniques as far as taking derivatives. In fact, we're going to be learning different techniques on taking derivatives off and on for the next month or so. So, like you have to take, basically it's going to be, I give you any function and you've got to take a derivative of it. And ideally you like when you can take the derivative term by term, but sometimes that's not possible, right? So today we're going to talk about a couple of cases where it's not possible to take the derivative term by term. And one of them is whenever you're multiplying two things together, like this, right? Here you could actually multiply them out so you can get term by term, but there are going to be some examples where you can't multiply them out, right? So we need a rule for when you're multiplying two functions together. And let's see. We're going to call my two functions f and g. So I've got f and I've got g. And I'll put the little prime up here. That means I want to take the derivative, and that's not showing very well on the monitor. And I want to talk about how do you take the derivative of f times g. Okay, I'll go ahead and tell you it's not f prime times g prime. It's a little more complicated than that. So there is a neat proof, and I could go through the proof. But as I've learned through the years, the actual physical proofs that you see in your textbook, I find them interesting, and maybe a couple of students find it interesting, but at the end of the day, it's not so interesting. There is a neat picture for this, and I do want to explain. I do want to talk about the picture. And when you're multiplying two things together, that's like a rectangle. Like if you multiply, like the area of a rectangle, right? Like this side and this side, you multiply them together. Oh, that's the area of the rectangle. So what if I name this side f and this side g? Right? Are we okay that the area of this rectangle is going to be f times g, which kind of relates to this, all right? But now I need to talk about, well, what does it mean to take the derivative, right? See, derivative is like rate of change. Another way of thinking of a derivative is how much something changes. It's measuring how, like your rate of change is how much something changes. So I'd like you to think of f prime is the change in f, meaning if f changed just a little bit. So if f changed just a little bit, that's going to be here, and I'm going to call that f prime. G prime is what if g changed just a little bit. So if g changed just a little bit, I'm going to call that g prime. All right? And what I'm interested in is the change of the area. Because f prime g or f times g is the area, and f times g prime is what's the change in this area going to look like. So, I need to do a better job board work. How far can I write to the left? So I'll say f times g prime. So now let's look at the change in area. If I look at the change in area, let's see, my rectangle grew this little bit, didn't it? So let's find the areas of the little bits that grew. What's the area of this rectangle?
F prime times g.
F prime times g, right? Okay, so this is f prime times g. What's the area of this rectangle?
G prime times f.
F times g prime.
G prime.
Yeah, or f g prime. Or g prime times f, right? And what's the area of that little rectangle? F prime times g prime, right?
Yes.
So if I wanted to kind of summarize that with, what's our change in area of f times g, this is f times g prime is what's the change in area, right? So our change in area is this bit. So I'm going to add it up. I'm going to say f prime g plus g prime f plus f prime g prime. Draw a little wall here so I don't get confused with the other f. Now, I'm going to do a whole lot of hand waving because this is not an official math proof, all right? Official math proof would involve limits and a lot more board space. This is just a picture, right? But my argument is, when I drew f prime, I had to really exaggerate it. The reason I had to exaggerate is just so I have enough room to write stuff in the rectangle, right? Same thing for g prime, right? I had to exaggerate those. Realistically, what's happening is g prime and f prime are really, really small. And if g prime and f prime are really, really small, this little guy is going to be really, really, really small, right? In fact, it's going to be so small, we're just going to think of that going to 0. So this doesn't matter. That f prime times g prime doesn't matter. Oh, look. We have, this is called the product rule, right? So what's it good for? Well, let's see. Let's look back at that first problem. Let's say I give you 3x minus 2x squared, and this is 5 plus 4x. If we look back at that first problem, do you see that we're multiplying two functions together?
Yes.
Right? Now, anytime you're multiplying two functions together, I'm going to do something that seems really childish, right? You think, this is so simple. I know we're in AP Calculus. Why on earth would you do something so silly? Well, here's why. It works, all right? And as you're going to find out very shortly, sometimes things get really, really complicated. And this silly little thing I'm going to ask you to do can make some things that are really complicated less complicated. And here's the silly little thing I want you to do. So has everybody written this down again? Okay. And everybody, it was the same one that we did. Yeah. It's the exact same problem. Here is the silly little thing I want you to do. Right? And the silly little thing is anytime you're multiplying two things together, I want you to draw a line in between them. Super silly, right? Why on earth would we need something so, ridiculous for AP Calculus class? Right? Because your teacher's crazy. Right? But drawing that line does a couple of things. One, it tells you that now we're going to use product rule. And of course we're using product rule, that's what I'm teaching today. But when I start teaching a bunch of other ideas, that idea of product rule gets further from your mind. So drawing that line reminds you that you're going to use product rule. And the second thing it does is it guarantees, oh, this is my f and this is my g. You easily identify what your f and your g are. And I realize y'all are all smart. You can do that without the silly line. But the silly line helps. All right, so let's look at our product rule. Product rule says f prime g, meaning the derivative of this times this. So when I take the derivative of this, well, the derivative of 3x is 3. Derivative of this is going to be minus 4x times g, which is going to give me 5 plus 4x. Right? So your f, everybody see this is your f prime and this is your g. Plus your derivative of g, which the 5 goes away, so the derivative of 4x is 4, times f. That gives us 3x minus 2x squared. So here's g prime, and here's f. And right now I look at this, and that does not look like the same answer I got on the warm-up. But we're not done. We got to clean all this up. So let's see. When I clean it all up, I get 15 minus 20 plus 12 is minus 8x minus 16x squared plus 12x minus 8x squared. And everything? Yeah. So minus 16 minus 8x is negative 24x squared. And minus 8x and 12x gives me a plus 4x, and I get a plus 15. And I really hope that was the answer we got at the beginning.
Yeah, that was.
Awesome.
Actually, I got negative 4x and then
I got
That's
to
what we- that's what we
negative
got.
20.
That's what I got?
Yeah, for the
Oh,
first
maybe I
time.
just wrote it down.
Oh, okay.
What?
Already messed up. I don't have another recording. I'm stuck with this. I've got to keep going.
Okay.
All right. Yeah, I messed up on this first problem, and at this point I just said canon, I'll just record 6th period. All right. So, couple of things. One, if
that's so good.
all right. Okay. So, a couple of things. If you look in your textbook, they have the product rule written a little differently, and you're going to see why I used f and g. Pretty much a lot of textbooks, they don't like f and g for some strange reason. They like u's and v's, and I'm going to show exactly why I don't use u's and v's.
I can't tell.
Can't tell the difference, right? U prime v plus v prime u is like, it doesn't take much that this gets super confusing very quickly, right?
Yeah.
So when you, like if you look in the book and you say, wait, why is he using f's and g's? Because my handwriting's terrible, right? I'm not saying my f and g are very neat, but at least they look different.
Yeah.
Okay. All right, so let's do a practice. We're going to do a practice product rule problem. So let's say if I give you y is equal to 2x cosine x. And I do apologize. Normally I would have made you practice taking derivatives. Are we okay with the derivative of, are we okay the derivative of sine is cosine x? And the derivative of cosine x is a negative sine x?
Go with that now.
Right? And I wasn't too worried about it Tuesday because after tomorrow you're going to be an expert at it. Because based on what I'm doing tomorrow. But I do need to make sure that you know the derivative of sine is cosine, derivative of cosine is negative sine. And I'm going to help you out here. Silly line. Oh, one thing about the line. When you draw the line, you better make sure there's x's on both sides. If there's not x's on both sides, I hit pause through that whole thing. All right, if you're watching the video, there's the answer, and I added part to it. It's all right, okay?
That's unfortunate.
Sorry, the first period, oh well. I thought I did a pretty good job teaching that too. Okay, there, so now, all right, so if you're talking about multiplying, we've got a product rule. What do you think's next? So if we're talking about multiplying functions, what do you think's next? Dividing. Guess what we're going to call that?
Dividing fractions.
Quotient.
Quotient, right? Think about it. The fancy word for multiplying is product, so the fancy word for dividing is quotient, right? And unfortunately, I don't have a clever picture for the quotient rule. I've looked for a clever picture of y. Oh, whoops, I left that up there. So f times g is going to be f prime g plus g prime f. And I have f over g. So I'm just going to give you the rule. It's going to be f prime g minus g prime f all over g squared. Now, a couple of things. First, let's talk about some similarities. Notice that the derivative of, when you're multiplying, you have f prime g and a g prime f, and you have the exact same thing in quotient rule. You have f prime g and a g prime f. Okay? Here's the problem, and this is the thing you have to be careful about. When you're adding, it doesn't matter. Because if I change the order, I'm still going to get the right answer. Because 2 plus 3 is the same thing as 3 plus 2. But in the quotient rule, you got to make sure you get the right order. And there's also this little thing in the bottom where you have a g squared. So let's look at an example. Let's say I have y equals y equals 5x minus 2 over x squared plus 1. Now, I clearly have a fraction, right? Because when you have a fraction, I actually need to be careful how I say this. But in this case, so I've got a fraction, I'm going to use quotient rule. And how I want you to think about the quotient rule is I want you to think of, when I look at this, I don't think of f and g. I think of top and bottom.
Thank you.
Sorry. So I think of top and bottom. Okay? And so when I look at this, when I look at the rule, I think it's derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So when I look at this thing, it's derivative of the top, which is 5, times the bottom, minus derivative of the bottom. So derivative of the bottom is going to give us 2x, and derivative of 1 is 0, times the top, all over the bottom square.
Are we fine leaving it?
No, you actually got to clean the top up. So a couple of things. Pretty much every quotient rule, you're stuck. You got to clean the top up. But you never, ever, 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 ever,
Oh, that's
ever multiply the bottom out.
That's fine.
Okay.
Wait, why did it go from x squared to negative 2x?
Well, the minus came from here. Okay? Right? This minus came from here. This 2x came from the derivative of the bottom. Right? Because this is my g. Okay? Derivative of x squared is 2x, derivative of 1 is 0. So that's, this is my g prime, this is my f, this is my f prime, and this is my g. Did that help?
Yeah, that's good.
Okay. All right. Well, and so now we've got to clean the top up. So clean the top up, I get 5x squared plus 5 minus 10x squared plus 4x all over x squared plus 1 squared. And my final answer, 5x squared minus 10x squared is a negative 5x squared plus 4x plus 5 all over that bottom squared, which is x squared plus 1 squared. Yay. Woohoo! All right. So obviously not done with this. We're going to practice a bit more. But I need to do something, and I should have done this last week, and I didn't. So I'm going to start it now. And there's a phrase that's going to show up a lot. It's going to be almost daily from now until the end of the year. All right? And this phrase is find the equation of the tangent line. Okay? This phrase is just going to keep showing up and up and up and up. And I'm going to be telling you right now, I hate writing all that out because every time it's the exact same thing. Now, this abbreviation is just for me. No book, no other teacher ever uses this. But I'm going to be saying find the equation of a tangent line so much, I want to make sure we got the same terminology. And so instead of writing out all of this every single time, I'm going to say find the equation of the tangent line. However you want to say it, right? But when you see this, obviously on a test, I would write this part out. But as far as giving examples, I'm just going to say this, and I'm just going to write this down, and it says find an equation of a tangent line. So, we're going to practice. Okay. 2y equals x over x squared plus 1 at x equals 2. So if I ask you to find an equation of a tangent line to this function at x equals 2, let's talk about finding the equation of a tangent line. So find an equation of a line. Just in general, to find an equation of a line, you need two pieces of information. You always need two pieces of information. You need a point and a slope. Whenever you're asked to find an equation of a line, and you will be asked many times in this course, when I ask you to find an equation of a line, you go, all right, I need a point and a slope. Right? Well, to find the point, if I give you the x value, it's pretty easy to get the y value, just plug it in. So if I plug y in, it's going to give me 2 over 5. So I have the point 2 comma 2/5. Now if I say tangent line, then you've got to take the derivative. And so when I take the derivative of this, I've got a fraction. I get to use quotient rule again. Yay! Derivative of the top is 1 times the bottom, which is 2x, which is x squared plus 1 minus derivative of the bottom, which is 2x times the top, all over the bottom squared. And let's see.
Forgot the square.
Thank you. X squared minus 2x squared is negative x squared plus 1, all over x squared plus 1. There's your y prime. To find my slope, I got to plug something in, right? The 2. And so when I plug the 2 in, I get negative 4 plus 1. It's going to give me a negative 3. 4 plus 1 gives me 5. There's my slope. There's my point. Point slope form. Y minus 2/5 is equal to negative 3/5 x minus 2. That's what I'm looking for. And there are going to be many, many times, like the way we work, the way calculus teachers do this is we practice taking derivative, and then at some point your application of taking a derivative is find an equation of a tangent line. It's just another thing. Okay, take a derivative, now use it, right? If you notice, I didn't do much more. The difference between this problem and the previous one was there's virtually not. The only thing I had to do was actually figure out the y value and then come up with a line. All right.
In the denominator, what happened to the being square?
Oh, shoot. I forgot it. It should be 3 over 25. Good job. I'm going to blame breathing this and trying to the air generate. That's what I'm going to say. It's if you could just sit without with a mask on, it's okay. But to teach, there's a lot of air. There's a lot of air trying to go through this little piece of paper. All right. So what I've just done is introduce the quotient rule. And what I'm about to do is actually almost as important as introducing the quotient rule. And what I'm about to do, which I'm going to claim is almost as important, is when you don't need to use the quotient rule, right? See, a lot of times, product rule is kind of obvious. You draw the line, you see x's on both sides, you got to use product rule. Quotient rule, now technically you can use, you can use product rule anytime you're multiplying. For example, if I give you 3x squared, you could use product rule on this if you really wanted to. Right? I don't know why you'd want to, but you could, right? Draw the line. Let's see, the derivative of this is 0 times x squared plus 3 times 2x, and so we end up with 6x, right?
But didn't you say that there has to be an X on each side?
There doesn't have to be,
Oh, okay.
but you have to use it when there's x on each side.
Oh.
If there's not an x on each side, it's like, you could do this, right? But did you really need to? No, you just do the 6x, right? A similar thing happens with quotient rule. The problem is nobody really overuses product rule. A lot of students overuse quotient rule. Example, if I gave you x squared plus 2 over 6, and I said take the derivative. See, what always happens is you go, anytime you see, it's like someone gets in their head, anytime you see a fraction, you have to use quotient rule. Right? Okay. And you could, right? You could use quotient rule on this, you would get the right answer, right? But your life is a lot easier if you look at this as, oh, this is really just 1/6 times x squared plus 2, isn't it?
Yes.
And anytime you've got a number that's multiplying, you could always think of that as decoration. So if you think of this as decoration, just ignore this, take the derivative of this thing, which is going to give us 2x. Our decoration is still here, so we get 1/6. And so my answer is just x over 3. Okay? What if I give you y is equal to x squared plus x all over x cubed? You got a fraction, right? Could you use quotient rule? Of course you could. But you don't have to. See, this is kind of related to what I did on Tuesday. Because could we break this apart and write it term by term? See, I can look at this and say this is x squared over x cubed plus x over x cubed, which gives me, I'm running out of room, gives me x to the -1 plus x to the -2. And so now when I take the derivative, I get negative x to the -2 minus 2x to the -3, which is minus 1 over x squared minus 2 over x cubed. I'm going through this quick because I know the bell's about to ring. Right? But here's the kicker. And this is the one every time I ask this on a quiz or a test. And I can't tell you how many people use quotient rule. What if I gave you square root of x over x squared and said take the derivative? Right? You could use quotient rule on this. Anytime you have a fraction, you could use quotient rule. And what happens when you try to use quotient rule in this is the problem gets about this big, and somewhere your algebra skills break down, and you end up with garbage for an answer. But what if you approach this problem the exact same way you'd have to do this that we did on Tuesday? Could you rewrite this as x to a power?
Yes.
See, that's x to the 1/2, that's x to the 2. This gives me x to the -3 over 2. Wouldn't you rather take the derivative of that
Yes.
as opposed to quotient rule and hope you could simplify?
Yes.
All right. Okay, good. I got 30 seconds. So the key is, right? I've introduced this thing called quotient rule. Sometimes you have to use it. Sometimes you don't, and we're going to talk more about that tomorrow. Your homework is out of your textbook. It's in OneNote. Please, please, please practice it, because if you don't practice that, what I do tomorrow is not going to be nearly as effective. Right? Because this is going to be sort of it's going to be an extension of what I did today. All right.